This is going to be the lecture over section 22.4. We're going to be looking at power in AC circuits. So the average power input to an AC circuit is going to be I times 1/2 the component of the voltage that is in phase with the current. So in other words, power is equal to 1/2 VI cosine of phi. It's also going to be equal to the voltage root mean square times the current root mean square times the cosine. Phi here is going to be the phase angle of voltage with respect to the current. Power is dissipated only through the resistor. For currents containing only capacitors and inductors, phi is going to be equal to plus or minus 90 degrees, and the average power is going to be 0. The quantity cosine of phi is also going to be called the power factor. So if we're looking at graphs of power, voltage, and current versus time for an arbitrary connection or a combination of resistors, inductors, and capacitors, this is what it's going to look like. It's a little busy. The average power here is going to be positive. So we're looking here, this is going to be the current here in purple. The voltage here is going to be in red. And then the power here is going to be this black line. So let's take a look here in this particular section. All right, we have to look at AC circuits because they play a central role in distributing, converting, and using electrical energy. So we need to look at the power of those relationships. So when a source with voltage amplitude V and instantaneous potential difference little v supplies an instantaneous current with the capital I as a current amplitude to an AC circuit, the instantaneous power P that it supplies is going to be this, which you have seen in chapters before. Again, the instantaneous current is going to be this modeled with this particular relationship. Let's suppose that the current consists of a pure resistance R. Then I and V are going to be considered in phase, which you remember that from previous section. If we graph that here for a resistor, again, this is what the voltage looks like. This is what the current looks like. And therefore the power, which is going to be the product of these two, is going to be positive when both are positive. It's going to be 0 when, in this case, both of them happen to be 0. The power is also going to be positive when both are negative. And since both are positive or negative at the same time, the power is always going to be positive when we're looking at a pure resistor. Things change when we start looking at inductors or capacitors. Again, this relationship is going to be the same, but it's also going to be alternately positive and negative. And the average power here, average power is going to be 0. So here you've got at the origin here, you've got V and I again. For pure inductor, you've got V and I with their relationships as they go through. Again, they're not peaking and valleying at the same time. They're out of phase with each other. Because they're out of phase with each other, you're going to see here you've got positive current, but you've got negative voltage, and that ends up giving you a negative power. When one of them hits 0, the power hits 0. Here at this particular spot, both are negative, which gives you a positive power. And you can see how the power relates as it goes through. On average, it's going to be running through 0. Same type of thing goes on here with a pure capacitor. It's just a little out of phase from what you're seeing over here. If, however, you have all kinds of combinations here within this AC circuit, what you're seeing here is a voltage, and you're seeing the current being described here for whatever it happens to be. The power here, of course, being the product of those two, is going to look like this. Instantaneous, it'll be at whatever point is along the line there. Here again, this is the relationship of the amplitude of the power and the voltage and the current. You can see the same thing over here. You got V of RMS, I of RMS, and that product here, you can see where the square roots kind of are taken care of, or they're involved because we're dealing with the root mean square, and that basically gets rid of the 1/2 here. So you can express power here in terms of I squared R. If I is the root mean square, you can represent that as the voltage of root mean square squared divided by R, or this. It depends. In many cases, it depends on what bit of information you have available to you at that time. Here's a description of application of too much power. For modern electronic equipment, it can be damaged irreversibly by abrupt changes in electric current, known as power surges. It's caused by nearby lightning strikes, by malfunctioning transformers, or by switching on a large piece of electrical equipment, such as a compressor or elevator, that can momentarily disrupt the line voltage. A common type of surge protector has a component called a metal oxide varistor, a variable resistor containing semiconductors, connecting the hot wire to the ground wire. At a normal line voltage, the varistor resistance is very high and current travels past it to the outlet. However, if the voltage exceeds a certain limit, the varistor resistance drops dramatically and the current flows through it directly to the ground wire, bypassing the outlet and protecting your electronic equipment from being fried. So next, we're going to look at this. We're connecting the source to a pure inductor. Again, if we also put in a capacitor, we know how the voltage leads the current in both of these cases. So here in this particular case, we are wanting to get an idea as to what the power is, regardless of what types of elements we have in the system. We know how the power and the voltage are varying with each other. We know that the voltage here is has some sort of phase angle in comparison to the current. We just don't know what that is at this particular point. If we want to get at arguments within a trig function and how we can break those out, we can use a trig identity. When we use that particular trig identity, we can rewrite these. I won't go through the mathematics here of how to do that, but this is what we can come up with. In the end of it all, this is ultimately what we come out with. When we do that, we can again rewrite V and I as far as the root mean square is concerned. Once we know what that particular angle is, then we can figure out what the actual power is. So you have some problems there and some tutorials to go through.